All right, let's go. Number 9, the neutrino. Predicted in 1930, discovered in 1956. In 1930, physics was facing an existential crisis. Scientists observing radioactive beta decay noticed something that should have been impossible. They measured the energy going into the reaction and the energy coming out, and the books didn't balance. Energy was disappearing. For a physicist, this is worse than finding a mathematical error. The conservation of energy is absolute. It's the foundation everything else stands on. If energy could simply vanish, then every equation, every theory, every prediction would be worthless. Wolfgang Pauli, an Austrian physicist, proposed what he himself called a desperate remedy. He wrote a letter to his colleagues, famously opening with "Dear radioactive ladies and gentlemen," and suggested the existence of a particle so elusive it bordered on theoretical fiction. This particle would have no electric charge, virtually no mass, and almost no interaction with ordinary matter whatsoever. It would steal the missing energy and slip away completely undetected. Pauli was so uncomfortable with his own idea that he reportedly said he had done a terrible thing by proposing a particle that could never be found. He even wagered a case of champagne that no one would ever prove it existed. 26 years later, he lost that bet. In 1956, physicists Clyde Cowan and Frederick Raines set up a detector beside the Savannah River nuclear reactor in South Carolina during what they called Project Poltergeist. They were hunting for ghosts. By watching for the extraordinarily rare moment when a neutrino actually interacted with a proton, they caught one. The phantom was real. But here's what makes the neutrino genuinely unsettling. Right now, this very second, roughly 100 trillion neutrinos from the sun are passing through your body. They're streaming through your eyes, your skull, your heart. They pass through the entire planet without touching a single atom. You're completely invisible to them, and they are nearly invisible to you. We exist in a constant bombardment of particles that treat solid matter like it isn't even there. When a star explodes in a supernova somewhere across the galaxy, the neutrino shockwave washes over Earth hours before we even see the light. We're living inside an invisible storm. Number 8, the positron. Predicted in 1928, found in 1932. Paul Dirac was trying to do something no one had successfully done before. He wanted to merge quantum mechanics with Einstein's special relativity, creating an equation that described how electrons behave at speeds approaching light. The math worked beautifully, but it had a strange quirk. Just like the equation x squared equals 4 has two solutions, positive 2 and negative 2, Dirac's equation spat out two answers. One described a normal electron. The other described something that shouldn't exist, a particle with the electron's mass but a positive charge instead of negative. Dirac had accidentally predicted antimatter. Most physicists thought it was just a mathematical ghost, an artifact of the equations with no physical meaning. Why would the universe bother creating mirror versions of everything? 4 years later, Carl Anderson was studying cosmic rays with a cloud chamber, a device where charged particles leave visible tracks through supersaturated vapor. He photographed something bending through a magnetic field. The curve told him it had an electron's mass, but it was bending the wrong way. It was positively charged. He'd found the positron, and antimatter wasn't theoretical anymore. It was raining down on us from space. Here's the nightmare scenario this discovery revealed. When matter meets antimatter, they don't just collide. They annihilate each other completely, converting 100% of their combined mass into pure energy. According to everything we know about the Big Bang, the universe should have created exactly equal amounts of matter and antimatter. They should have immediately destroyed each other in a blinding flash, leaving behind nothing but photons in an empty void. But we're here. Something went wrong, or rather, something went incredibly right. For reasons we still don't fully understand, there was a tiny imbalance. For every billion antimatter particles, there were 1,000,000,001 matter particles. After the annihilation, that single leftover particle per billion is what built everything. Every star, every planet, every atom in your body exists because of a cosmic accounting error we can't explain. The positron proved we're living in the leftovers of a war between matter and antimatter, a war that by all logical reasoning we should have lost. Number 7, the gluon. Predicted in the early 1970s, confirmed in 1979. Look at the nucleus of any atom and you'll see an obvious problem. Protons are crammed together in an impossibly tiny space. They all carry positive electric charges. Positive repels positive. The electromagnetic force should blow the nucleus apart instantly. Every atom in existence should detonate, but they don't. In the early 70s, quantum chromodynamics provided the answer. There had to be another force, something stronger than electromagnetism, something powerful enough to overpower the repulsion and glue the nucleus together. They called it the strong nuclear force, and its messenger particle was the gluon. In 1979, scientists at the Petra Collider in Germany smashed electrons and positrons together at extreme energies. They couldn't see gluons directly. You never can. But they observed what's called a three-jet event. When the particles annihilated, they sometimes produced a quark, an antiquark, and a third distinct spray of energy. That was the gluon radiating away. The glue was real. Here's what's disturbing about gluons. If you add up the mass of all the individual quarks inside the protons and neutrons in your body, it accounts for roughly 1% of your weight. Where's the other 99%? It comes from the binding energy of gluons. You're not made of solid matter. You're made almost entirely of the furious energy of massless particles moving at light speed, desperately holding your fundamental components from flying apart. If gluons stopped working for even a fraction of a second, you wouldn't explode. You'd simply cease to be coherent matter. The universe would unravel into formless radiation. What makes this even stranger is that the strong force is unimaginably powerful, but only at distances smaller than an atomic nucleus. Step outside that range and it vanishes completely. It's like a lock that only works when you're already inside the prison. Number 6, the W and Z Bosons. Predicted between 1967 and 1968. Discovered in 1983. For centuries, the sun was an impossible object. How could something burn for billions of years without consuming itself? The answer was nuclear fusion, but fusion had a problem. It required protons to transform into neutrons. That transformation is controlled by the weak nuclear force, the mechanism behind radioactive decay. But forces need messengers. Electromagnetism has photons. The strong force has gluons. What carried the weak force? In the late 1960s, 3 physicists independently arrived at the same radical conclusion. Sheldon Glashow, Abdus Salam, and Steven Weinberg proposed that electromagnetism and the weak force weren't separate. They were 2 aspects of a unified electroweak force. The math was elegant, but it demanded something specific. 3 massive messenger particles had to exist: the W+, the W-, and the Z boson. Finding them would require extraordinary energy. In 1983, CERN's super-proton synchrotron accelerated protons and antiprotons to velocities approaching light speed and smashed them together. In those violent collisions, the W and Z bosons flickered into existence for a fraction of a second before decaying. They were real. But their discovery revealed something deeply unsettling about the universe's construction. These particles are absurdly heavy. A Z boson weighs about 100 times more than a proton. Because of quantum mechanics, that massive weight translates to an impossibly short lifespan. They exist for roughly a trillionth of a second. That's why the weak force only operates at microscopic distances. Here's what keeps physicists awake. Without the W boson, the nuclear reactions powering every star in the universe would stop immediately. The cosmos would go dark. But if these bosons were just slightly lighter, stars would burn out in millions of years instead of billions. Life would never have time to evolve. We exist because these unstable particles have exactly the right mass, flickering in and out of reality at precisely the correct rate to keep the universe alive. Number 5, quarks. Proposed in 1964. Experimental evidence in 1968. By the early 1960s, particle physics was drowning in chaos. Powerful new accelerators were discovering exotic particles faster than anyone could categorize them. Scientists called it the particle zoo, and it was humiliating. The universe was supposed to be elegant, not a random collection of subatomic debris. In 1964, Murray Gell-Mann and George Zweig independently proposed a solution. What if protons and neutrons weren't fundamental? What if they were composite objects made of smaller, truly indivisible particles? Gell-Mann named them quarks, borrowing the word from James Joyce. The theory had a bizarre requirement. Quarks had to carry fractional electric charges, like 2/3 or -1/3. Nothing in nature had ever shown fractional charge. It seemed absurd. Then in 1968, the Stanford Linear Accelerator built a 2-mile electron gun and fired it at protons. Instead of passing through or bouncing off smoothly, the electrons scattered at sharp angles. They were hitting something hard inside. The proton had structure. It had components. The quarks were real. But proving quarks exist opened a door to one of the most frustrating concepts in physics: quark confinement. You cannot isolate a single quark, ever. The strong force binding them together behaves like a rubber band. Pull two quarks apart and the force doesn't weaken. It strengthens. Pull hard enough and the bond snaps. But instead of freeing the quarks, the energy of the snap converts into mass, creating two new quarks from nothing. They immediately pair up. This is the ultimate prison. The fundamental components of reality are locked away behind an unbreakable law. We're made of quarks. Everything around you is made of quarks. But the universe has forbidden us from ever seeing one alone. Reality censors itself at the deepest level. Number 4, the pion, predicted in 1935, found in 1947. Before we understood quarks and gluons, physicists were trying to figure out the mechanics of the nucleus. If protons and neutrons are bound together, something had to be carrying that force between them. In 1935, Japanese physicist Hideki Yukawa calculated that a particle with a mass between an electron and a proton had to exist. He called it a meson. It was pure mathematical prediction with no experimental evidence. World War II interrupted the search. But in 1947, a team led by Cecil Powell tried something different. Instead of building expensive machines, they went to nature's particle accelerator. They coated glass plates with photographic emulsion and carried them to mountaintops in the Andes and Pyrenees, exposing them to cosmic rays from deep space. When they developed the plates, they found the decay tracks of a new particle, the pion. Yukawa was right. The discovery of the pion through cosmic rays revealed something most people don't think about. Space isn't somewhere else. We're not separate from it. Right now, high-energy protons accelerated by exploding stars and black holes are slamming into Earth's upper atmosphere at near light speed. When they hit atmospheric atoms, they shatter them, creating cascading showers of particles including pions. These showers penetrate buildings, pass through your skull, and deposit radiation in your cells. You are constantly being bombarded by the debris of stellar explosions happening millions of light years away. The pion proved we're not observers of cosmic violence. We're participants, whether we realize it or not. Number 3, the top quark. Predicted in 1973, found in 1995. As the Standard Model developed, physicists hit a mathematical wall. To explain why matter exists at all, why it wasn't perfectly canceled by antimatter, they needed asymmetry. 2 generations of quarks weren't enough. In 1973, Makoto Kobayashi and Toshihide Masukawa showed the math only worked with a 3rd generation. The bottom quark appeared quickly in 1977. The top quark vanished into the search for nearly 2 decades. Finally, in 1995, the Tevatron at Fermilab generated enough energy to create one. What they found was terrifying. The top quark is inexplicably massive. A single top quark weighs as much as an entire gold atom. An indivisible point particle with 0 volume somehow carries the mass of hundreds of protons and neutrons. Because it's so heavy, it's catastrophically unstable. It exists for about 5 times 10 to the negative 25th seconds. Light can't even cross a proton's diameter in that time. The top quark decays before it can bind with anything. It's a ghost from the Big Bang's first microsecond, a monster that shouldn't exist in our cold universe. Number 2, the Higgs boson, predicted in 1964, discovered in 2012. This was the final piece, the keystone holding reality together. By the 1960s, quantum mechanics had a catastrophic problem. The equations worked beautifully, but they insisted that every fundamental particle should be massless. Everything should race through space at light speed. If that were true, atoms couldn't form. Chemistry wouldn't exist. The universe would be an empty flash of radiation. But you have mass. The chair beneath you has mass. Why? In 1964, Peter Higgs and several colleagues proposed something invisible, permeating every cubic inch of space. Picture the universe filled with thick cosmic molasses. As particles move through this field, they experience resistance. That drag is what we call mass. To prove this field existed, scientists needed to find its particle, the Higgs boson. It took 48 years and the most complex machine ever built. The Large Hadron Collider at CERN, a 17-mile ring buried beneath the French-Swiss border. In July 2012, physicists who'd spent their entire careers searching finally found it. Some wept during the announcement. The media called it the God particle, which annoyed scientists endlessly. But discovering the Higgs field revealed something far more unsettling than its nickname: vacuum decay. Fields want to settle at their lowest energy state, like water flowing downhill. We assume our universe's vacuum is at the bottom, but calculations involving the Higgs boson and top quark masses suggest we might be sitting in a false vacuum. The ball hasn't reached the valley floor. It's resting in a shallow dip on the side of a cliff. If a high-energy event nudges the Higgs field out of this dip, it would fall to the true minimum. A bubble of true vacuum would appear and expand at light speed in all directions. Inside that bubble, the fundamental constants of physics would change. Electron masses would shift. Atoms would disintegrate. Every star, planet, and living thing would vanish. Because the bubble moves at light speed, we'd never see it coming. The Higgs boson explained why we exist, but it also revealed the knife edge our reality balances on. Number 1, the graviton. Hypothesized, never observed. We've mapped invisible mass fields. We've shattered protons. We've caught ghost particles streaming from the sun. But the most obvious force in existence, the one pinning you to Earth right now, is the one that shatters our understanding completely. Gravity is the gaping hole in the standard model. Electromagnetism, the strong force, the weak force. They all fit quantum mechanics perfectly. They're quantized, transmitted by messenger particles, but gravity, as Einstein described it, is smooth and continuous. It warps space-time itself like a stretched rubber sheet. Quantum mechanics is chunky and probabilistic. When you try merging quantum math with gravity at microscopic scales, the equations explode into nonsense, infinite values, mathematical gibberish. To fix this impossible gap, physicists proposed the graviton, a massless particle carrying gravitational force. But we've never found it. It remains a phantom haunting theoretical physics. The reason we haven't found it exposes our ignorance in the starkest terms possible. Gravity is absurdly weak. The entire planet Earth, 6 septillion kilograms of rock and iron, pulls down on a paperclip. But a tiny fridge magnet lifts it effortlessly. A magnet overpowers an entire planet without breaking a sweat. Why is gravity so pathetically feeble compared to the other forces? The terrifying answer might be that gravity isn't weak at all. We're just not experiencing its full strength. String theory and brain cosmology suggest something radical. While electromagnetism and the nuclear forces are locked to our three-dimensional reality, gravity isn't. The graviton might be leaking out of our universe, bleeding into hidden dimensions folded around us that we cannot see or touch. What we experience as gravity's gentle pull might be the faint echo of a much stronger force operating in dimensions beyond our perception. The graviton's absence might be the universe telling us our view of reality is fundamentally limited. We're trapped on a three-dimensional surface, watching shadows of higher dimensional physics play across the cosmos, completely unable to grasp the true structure underneath. We can detect the cosmic microwave background from 13.8 billion years ago. We can measure gravitational waves from colliding black holes across the universe. Yet we cannot find the particle that allows you to stand on solid ground. The graviton is the ultimate reminder of human limitation. Every other force has revealed its secrets. Gravity alone refuses. It suggests the universe isn't just stranger than we imagine. It's stranger than we can imagine. These particles aren't just abstract physics. They're the hidden machinery running beneath everything you see and touch. The Higgs boson gives you mass. Gluons hold your atoms together. W and Z bosons power the sun above you. Quarks build every solid object in your world. The top quark threatens vacuum stability. The graviton, still missing, governs your relationship with the planet beneath your feet. You are not separate from particle physics. You are particle physics. Every breath, every heartbeat, every thought firing through your neurons is these invisible particles interacting according to rules we barely understand. The Standard Model is humanity's most successful theory. It predicts experimental results to staggering precision, yet it's incomplete. Dark matter isn't in it. Dark energy isn't in it. Gravity doesn't fit. The neutrino masses don't make sense. We've built machines spanning miles underground, smashing particles together at near light speed, desperately searching for answers. We've sent detectors deep into mines to catch particles that barely exist. We've pointed telescopes at the cosmic microwave background, looking for clues in the universe's baby picture. And we've found wonders. Proof of antimatter, confirmation of the Higgs field, evidence of neutrino oscillations. But every answer spawns new questions. Why does the Higgs boson have the mass it does? Where did all the antimatter go? What gives neutrinos mass? What is the graviton, and why can't we find it? The particles we've predicted and found have revealed a universe far stranger than anyone imagined a century ago. A universe where solid matter is mostly empty space, where invisible fields give everything mass, where particles wink in and out of existence, where the vacuum itself seethes with energy. These discoveries didn't just change physics textbooks. They changed what it means to exist. You are not solid. You are not permanent. You are a temporary arrangement of quantum fields held together by forces we're still struggling to fully understand. The Standard Model is humanity's crowning achievement and its greatest humiliation wrapped into one. It predicts particle behavior with absurd precision, yet gapes with obvious holes we can't fill. Dark matter isn't explained. Dark energy makes no sense. Gravity refuses to cooperate. Neutrino masses shouldn't exist according to the original equations, yet they do. We've built underground cathedrals of science, 17-mile rings of superconducting magnets, detectors buried miles beneath mountains, all to glimpse particles that exist for less than a trillionth of a second. We've succeeded beyond what anyone thought possible a century ago. We found antimatter. We confirmed the Higgs field. We caught neutrinos changing flavor mid-flight. But every answer births new mysteries. Why these masses? Why this imbalance between matter and antimatter? Why is gravity so weak? Where is the graviton? The particles we've discovered haven't just rewritten physics. They've rewritten existence itself. You're not made of solid stuff. You're quantum fields temporarily arranged in patterns, held together by forces operating at scales you'll never directly perceive. The chair supporting you is mostly empty space. The light illuminating this room is particles and waves simultaneously. The vacuum around you seethes with virtual particles blinking in and out of reality. Physics predicted these particles through pure mathematics, then hunted them down in the debris of particle collisions and cosmic ray showers. Some took decades to find. One still hides completely. Each discovery proved the equations weren't just abstract symbols. They were maps to invisible machinery operating underneath everything you touch and see. That machinery is reality, and we've barely begun understanding how it works.
Please like and subscribe.
3 likes.